Okay, so we're all living through this incredible AI revolution, right? It's all powered by these deep neural networks that are creating just mind-blowing images and text. But there's a hidden cost. There are some really deep-seated problems brewing just under the surface. So today, we're going to dive into a pretty radical new framework that tries to tackle these issues head-on. So it's kind of like a tale of two AIs. On one side, you have our current champions, neural networks. Think of them as super powerful, but they're total black boxes. They can be fragile, they are incredibly hungry for data, and they're stuffed with billions of parameters we don't really get. But then on the other side, you got this new challenger, operator-based AI. And this approach, it's promising transparency, efficiency, robustness. It's not just a new model, it's a whole different way of thinking about building intelligent machines.
All right, so let's dig into that problem a little deeper. Models like CNNs and transformers, they've done amazing things, no doubt. But the very thing that makes them so powerful, their incredible complexity, is also their biggest weakness. Because they're so tangled and intricate, it's almost impossible to truly understand what's going on inside. And that, combined with their just endless need for more data and more computing power, is exactly why researchers are starting to look for a smarter way forward.
And you know, this quote from the research paper itself just hits the nail on the head. A massive parameter count. That literally means billions of tiny knobs being twisted and turned in a brute force effort. But the real danger here is the lack of interpretation. It means if an AI denies you a loan or maybe misdiagnoses a medical scan, we can't actually ask it why. And in really high-stakes situations, because the model said so is just not a good enough answer. And that, right there, leads to this really fascinating, kind of radical question. As a response to all these problems, what if we've been thinking about machine learning all wrong? What if instead of just building bigger and bigger models with more knobs to tweak, the real solution is to find the perfect mathematical transformation for any given task? Okay, let's break that down. A neural network learns by just hammering away, adjusting billions of weights until it stumbles upon the right answer. This new idea completely flips that script. Imagine you've got an audio clip you want to turn into text. Instead of a tangled mess of billions of connections, what if you could find one single elegant mathematical machine that does that exact transformation perfectly? And this is the big idea, the core leap in thinking. You have to stop thinking about data as just a pile of pixels or numbers. Instead, we start to see everything, an image, a sound wave, a sentence, as a mathematical function. And when you do that, the goal of learning totally changes. It's no longer about tuning parameters. It's about finding the perfect operator, that one precise rule that maps your input function to your output function. Okay, but to make this actually work, our functions need a place to exist, a sort of mathematical playground, if you will. And this is where the theory gets, well, really beautiful, honestly. We're about to step into the world of Hilbert spaces, and this is where the magic really starts to happen. Now, don't let the name intimidate you. The easiest way to think of a Hilbert space is as this massive, infinite library. But instead of books, the shelves hold every single function you could possibly imagine. Literally, every photo ever taken, every song ever recorded, every radio signal from a distant star, they all exist as a unique point, a unique function inside this space. So if the Hilbert space is the library, then an operator is like a magical machine inside that library. You can feed it one function, let's say a blurry photo, and it applies a very precise, well-defined rule to transform it into another function, the perfectly sharp version of that photo. So instead of that tangled web of a billion neural network connections, you get one single, clean mathematical concept. And the goal is just to find the right one for your specific job. So how does this actually work? Well, the process itself is surprisingly clean, really just 3 steps. First, you take your data, every image, every sound, and you represent it as a function inside that infinite library, the Hilbert space. Second, you use your training data to figure out the single best operator, that one transformation machine that consistently turns your inputs into your outputs. And finally, you just apply that learned operator to new data, and it transforms it with pure mathematical precision. I know this all sounds incredibly elegant, right? But theory is one thing. The real billion-dollar question is always, does it actually work? Can all this mathematical purity really compete with the raw, brute force power of today's giant neural networks? Well, let's take a look at the evidence. Well, the paper lays out three awesome examples to show this thing in action. First, you've got scattering networks, and the incredible thing here is they use these mathematically derived filters that need zero training at all to analyze images and sound, and they're super robust by design. Then there are Kopman operators, which are amazing for finding simple, linear patterns inside incredibly complex, chaotic systems like weather. And then, most recently, you have these spectral dictionary models, which are going toe-to-toe with the best transformer models on their own turf, vision and language. And when you actually put them head-to-head with neural networks, the results, they're seriously impressive. In some cases, like classifying textures when you don't have a lot of data, these methods are actually better than standard CNNs. For predicting chaotic systems, they're more stable, but honestly, this last one is the real jaw-dropper. A new vision language model built this way gets 85% of the way to a top-tier competitor while being dramatically smaller. Yeah, let's just pause on that number for a second. 60% fewer parameters. That's not just a small improvement. That is a game changer. That means a model that's way smaller, much faster to train, and a whole lot cheaper to actually run. For anyone building this stuff, that means real-world savings and accessibility. This is that promise of efficiency becoming a reality. Okay, so let's zoom out. What does all of this really mean for the future of AI? This operator-based framework isn't just some interesting idea from a lab. It really feels like a genuine alternative path forward, a way to build a totally different kind of intelligence. And what's so cool is that the big wins here directly attack the very problems we talked about at the beginning. Because the model is the math, you get actual interpretability, not just some guesswork. You get these really compact models with way fewer parameters. You get mathematical guarantees of stability and robustness baked right in from the start. It's a path toward AI that could be not only powerful, but also a lot more trustworthy. Okay, but let's be real. This isn't some magic bullet, right? There are definitely some big hurdles to overcome. A model's success really depends on choosing the right starting set of functions. It's kind of like trying to paint a masterpiece. If you choose the wrong primary colors to start with, it's going to be tough. And trying to replicate that wild, nonlinear creativity that makes neural networks so powerful is still a challenge. And so is scaling this up to handle massive data like video. So, at the end of the day, this isn't really about replacing neural networks entirely. The idea isn't to just throw them out. It's more about building a complementary path. It's about creating a richer, more diverse AI toolbox so we can choose the right tool for the job. Sometimes that might be the massive black box, but other times it might be an elegant, transparent, and mathematically solid operator. And that leaves us with a final, really provocative question to think about. For the past decade or so, progress in AI has pretty much followed one simple rule. Bigger is better. More data, more parameters, more computers. But maybe, just maybe, the next great leap forward won't come from just scaling up. Maybe it'll come from getting smarter, from building on a foundation not of brute force, but of better, more elegant math. What do you think?